Hello everyone and welcome to episode 4.1 of Particles in a Box. Today we're going to be doing some integration problems. So we're just going to be building off of what we were doing last time. I went over some integrals and the basics and a little bit of the theory. And so today we are going to be exploring some applications and what I deem as some interesting problems. So without further ado, let's get going. Okay, so in this first example, we just have what might look like a somewhat interesting integral. I got the integral of 1 over x to the 4th times the square root of 9 minus x squared. Okay. So I'd be thinking, okay, well, what's a good way to approach this? Well, it turns out the best way to do this is through a trig sub. Okay. So again, if you don't remember trig sub, go back to the trig sub section of the last episode. So you find dx, pretty simple. And then you just go ahead and you plug in all of your stuff. So you have your dx here, right? So that's where this 3 cosine of u comes from. And then you plug in all of your stuff for x. And so you just do a series of simplifications, okay? And you eventually get, you factor out your 9 here, right? And you get 1 minus sine squared of u, which is just cosine squared u, which is really nice. When you take the square root, you get your cosines to cancel. So when you're all said and done, you get to this cosecant to the 4th power of u. And so what makes this problem interesting, right, is we just did trig sub, okay? But now we actually have to do another substitution with v to the cotangent of u. So what we ended up doing is we took cosecant to the 4th, we split it up into cosecant squareds, and it turns out that cosecant squared is equal to cotangent squared plus 1. So that's just a trigonomic identity. If you have doubts on whether or not that's true, you go ahead and look it up. And so we're going to, instead of using u, we already used u, we're going to use v. And so we're going to set v equal to cotangent of u. The derivative of cotangent is negative cosecant squared. Okay, so now it's almost like, okay, this is why we're doing this. Okay, that makes more sense. So then when you end up plugging in for du, your cosecants end up canceling. And you just end up with v squared plus 1, which is something that we know how to take the derivative of. And so you get your nice little polynomial, right? And then you can plug back in your cotangents, and you can get something like this. Okay, which is great. The problem here though is we're still in terms of u. Okay, we started with x's in our original problem, so we're back to u's, but we're not back to x's yet. So we know that x is equal to the that is not going to be helpful. X is equal to 3 sine of u, and so sine of u is equal to x over 3. Which is the opposite over the hypotenuse, again, using your trigonomic definitions. So you can figure out what the adjacent is, and you can figure out the cotangent of u is the adjacent over the opposite. So remember, cotangent is equal to 1 over tangent, okay? So instead of opposite over the adjacent, it's the adjacent over the opposite. And once we know that, we can plug this in for all of our u's. And or all of our cotangent u's, I should say, and you get some nice big long expression. You can't really actually simplify this too much because you have a cubed of a square root. You can't really simplify that. You could write it to the 3/2 power if you wanted, but I mean it's not gonna help you out too much. So yeah, I picked this example because you have to do a trig sub, and then you kind of have to do another trig sub / a u sub, right? So, just a reminder that, you okay, if you do a substitution, it may not have gotten you the answer right away, but maybe there's another substitution that you can make. So just a reminder that more than one substitution is allowed, and that is something that you can do. The other thing that I will say is to not forget about your multiplicative constants that might be needing to be carried through. It's really easy to have drop this 81 somewhere along in the process, and obviously that wouldn't be good on an exam or something. You lose a couple of points if you drop that. So I'll always make sure to carry your constants through. So for our next problem, we're going to do an integration by parts example. So we have the integral of x squared e to the x dx. So what we're going to do is we're going to find our u and our dv's. Okay, so we're going to let u equal x squared and dv equal e to the x. And so we know that du is 2x dx and v is equal to e to the x. So we go through and we plug in our values. So we get an x squared e to the x minus the integral of e to the x times 2x dx. Okay. Okay, so this is an integral. Well, how do I do this integral? It probably doesn't jump to you off the page, and it turns out, well, you probably can't just look at it and do it. You actually need to do integration by parts again. Okay, so so now we're going to evaluate this integral. I just changed the 2x and e to the x because it's better to use h, as in this case, h or your u. I don't want to use u twice, right? That's going to be confusing. So we use h. So h is going to be 2 to the 2x, and then dh is then 2 dx, right? So now you can see, like, okay, now we don't have any more x's in this dh. That's nice, right? That's kind of a hint that you're moving in the right direction. And then we still have our e to the x's out here. So we just use some different variables, right? And you can go through and find out what your integral is. Okay, so this evaluates to this, and then you can plug that in back up here, and you end up getting, once you distribute through the negative, you end up getting something pretty nice right here. So again, this is a reminder, you can do something twice, right? You know, if you want to be fancy, right, you could try to derive an expression for like e to the a, e to the bx, right, dx. You can integrate this, and you can do integration by parts a number of different times, right? I mean, all you have to do is get this a down to 0, right? So you keep doing integration by parts over and over again, and once you get your a to 0, then you're done, right? You're just going to be left with some constant. So you can drive a generic expression for that if you want to. I guess that's kind of a bonus problem. So yeah, another example that I thought was worth mentioning. Okay, so now here's one of the problems that people often, especially in calculus class, have a lot of trouble with. I'm just giving one example here, but if you're more interested in this and how like volumes work and whatnot, you can look up more examples or look at some other videos, and they'll go more in depth. But it's the idea of, well, if you have a graph of something, right? And in this case, in this example, I'm using the square root of x, and you revolve it around the x-axis, you end up getting a shape which is similar to the shape that I have on the right, okay? So you kind of can see, like, the outer part here is the square root of x. Maybe I should use a different color so it pops out a little bit more, right? You can see that there's kind of like the square root of x shape here. It's not like super noticeable, but you know, the outside is just defined by the square root of x. It's just revolved around the x-axis a bunch of times. So, so how you can approach something like this, right, is you can think of, well, this is like pretty circular, right? So I'm going to define there's a circle at some fixed value of x, okay? So at some x value, you can just draw a circle inside of here, okay? And that circle is going to have a radius, and I think I should use green here again, otherwise probably not going to be able to see what I'm doing. So you have some sort of circle in here, right? That circle is going to have some radius, okay? And you can find the area of that circle, and the area of that circle is pi r squared, okay? Well, we actually know what the radius of this, of what this circle is. It's the square root of x, right? So you have a square root of x right here, and if you think about it, right, the x-axis just goes straight through the center of this, right? So the distance from here to there is the square root of x, okay? And then down here, you can think of it as having the negative square root of x, right, at the bottom, okay? So you can just plug in for your radius, you can plug in the square root of x. And what you can do is that if you want to solve for the volume of this, you can just add up a bunch of these areas, okay? So you have your circle, right? Which is an area, and then you have an infinitesimal dx that adds a little bit of thickness onto that circle. That's an infinitesimal amount dx. So as you sum over all these infinitesimally small parts that each have an area, it's going to give you a volume. Okay. And the example that I did, we're going from x equals 0 to x equals 4. And so when you end up computing the integral, you get 8 pi. Okay, so the volume of this region that I have over here on the right is 8 pi. Another good way to check this, right, is that do we get units of volume? Well, yes, we have an area times a length, and an area times a length gives you a length cubed, and your units work out. Okay. So things to like farther applications of this, right? Well, instead of square root of x, you could have just had a line, right? You can revolve that around the x-axis. You can also revolve around the y-axis. So that's also something that you can do. And so the hardest part about this for most people is you have to kind of have to visualize like what's going on in your head. And if you have like some crazy function or something that, and you're trying to find the volume of it as it's revolved around the x-axis, it can get hard to visualize that. And, you know, it's one of these things where if you take a calculus class, right, you'll do a lot of examples, you'll do a lot of these, and having that intuition just helps you out in the long run. So, yeah. Okay, so now going on to another example here. So what we're going to be doing here is we are going to be trying to find the volume of this pyramid, okay? And the pyramid is defined by these points up here. So like the point nozzle up here, 0, 0, 1, right? And then we have our four base points, okay? So we go from -1 to 1, and we go from -1 to 1. Okay. So how do we go about doing this, right? Like what's the best approach and what's the best way of doing this? Well, the first thing I'm going to tell you is that there are actually 4 different ways to solve this problem. Okay. So you might be thinking 4 different ways. How is that even possible? Well, well, you'll see why in a minute. So the best way for me to go about this, right, is I don't want to integrate over this whole region at one time, right? That can get a little bit confusing, and there's more likelihood that you can make a mistake, okay? So what I did over here on the right is I just took a quarter section of this, right? So I took one of these triangular faces, right? And I put it up over here, right? And the way that I have this set up is that this is 0, 0, 1. So that's our top point. This is 1, 0, 0. And this is 0, 1, 0. Okay, so we're in the first quadrant of the XY plane, and we're in the positive Z. Okay. So the idea behind this is that if we find the volume of this section, we can just multiply it by 4, and we get the total volume. Okay, so that's why this is useful. Okay. So if I go to the next slide, there's going to be a lot of math. I've given you a fair warning, but we're going to break down each section, and in the end, you'll hopefully have a good understanding of why there's 4 different ways you can do this problem and how each one is slightly different from all the others. Okay, so a lot of math. So let's take it slow. Okay. So first of all, we got a 4, right? I said if we find the volume of the one region, we can multiply it by 4 to get the volume of the entire pyramid. Okay. And we have a triple integral here. Okay. So triple integral. Okay, we're finding a volume. Okay, that makes sense. Okay. We just have a 1 in here, right? There's no like weights or like density thing that we're doing, right? It's just 1, so that checks out. And we have our z, y, and x. Okay. So now comes the hard part, right? We need to find our bounds for our integration, okay? So When we go back, right, if you take a look at this, right, you have some sort of dy, you have some sort of dx, right, and you have some sort of dz that goes upwards. Okay, so dz, right, goes from the base to upwards, right, and then it hits the face. Okay, and so it can hit the face at different points, right? But it'll hit the face at some point, okay? And so, okay, well, so what is a face? Well, a face is a plane, okay? So what we need to find is we need to find an equation of a plane, because z is going from 0 to whatever the equation of this plane is, okay? And so if you look up here, right, I have the plane of this face, right? And it turns out that the equation of this plane is z is equal to negative x minus y minus 1. Okay. Well, you might be wondering, well, how would I know that, right? Well, like I said, we had 1, 0, 0. We had 0, 1, 0, and 0, 0, 1. Okay. So if you think about this, right, the equation of this line right here is z is equal to negative y plus 1. Okay. The equation of this line is z is equal to negative x plus 1. And then the equation of this line is y is equal to negative x plus 1. Okay. Okay, well, that's great. We have the equation with some lines. How do I combine this? And again, this we're taking a multivariable class probably would help. But if you kind of just think about it a little bit, right? You can kind of come up with this thinking that, well, okay, if x and y are both 0, right? That's plus 1. If x and y are both 0, right, I should get 1 up here. Okay, so that checks out. If x is 0 and y is 1, I should still get 0 because I want to be down here. Okay, that checks out. If I plug in a 1 and a 0, I should also get 0, so I should be down here. Right? If I plug in 1/2 and 1/2, I should still be at 0, which would be down here, right? And so you can kind of just like, okay, right? Like I plugged in a couple of points, right? Some major ones. It feels like it's working. Cool. Okay, I'm pretty sure I have an expression for this plane. Okay. So that is that gives us our first bound, right? Z goes from 0 to the plane. Okay. Then what we need to do is need to figure out some limits for y, right? And if we go back, right, I said that the equation of this line here was y is equal to negative x plus 1, right? So rewind a couple of seconds if you missed that. So we now have our other bounds, 0 to negative x plus 1. And then our x point goes from 0 to 1 in the quadrant that we're in. Okay. So we've set up so we found our limits. Okay. And we're going to multiply by 4, like I said, because this is one of 4 quadrants. So we're just going to multiply by 4. And so now we're just going to go ahead and evaluate this. Okay. So the first integral that we're going to be doing is just 1 dz with our limits, right? And that's just going to spit us out an expression. Okay, then we're going to go to our second integral, and we're going to get this antiderivative. Okay, remember, we treat the x as a constant since we're integrating with respect to dy. 1 is just a constant of itself. So you get negative xy minus 1/2 y squared plus y evaluated at our bound 0 and negative x plus 1. Okay, so you go ahead and you plug all that in, you simplify it down, and oh, that's interesting. You get a 1/2 times the quantity negative x plus 1 squared. Okay, well that is quite interesting. It might not be interesting to you, but that's what we get. And what that allows us to do is we can plug that into our last integral, 4 times the integral from 0 to 1 of this quantity, right? You end up getting this 2, right? 4 times 1/2 is 2, so that's where you get the 2. You expand this out, makes doing the integral a little bit easier, right? And then you get this thing right here. And so you end up getting 2/3. So the volume of our pyramid is 2/3. Okay. So now you might be wondering, okay, well, okay, that's, you said there was 4 ways to do it. I see some other boxes here. So what's going on? Like, how is there more than one way to do this? Okay, so I'm going to drop this down here. So the next way you can think of doing this, right, is with a single integral. Okay, well, how would we do that? Well, what you can do is you can take a look at this, right, and you can see that there's like a big triangle right here. Okay, and so this triangle has an area. Okay, the formula for the area of a triangle is 1/2 base times height. Okay, so the height, right? What is the height? Well, if you rewind a little bit, I said that the equation of this line over here was -x plus 1. Okay, so you go from the base to this line, and that is one of your coordinates. Okay. Okay. Well, what about the height? Right. What about the, well, I guess this is the height. This is the height. That's height h. So what about the base? Right. What does the base do? Well, the base goes from the x-axis to this line right here, which if you rewind, it was y is equal to -x plus 1. Okay. So that's our base. Okay, so now we have a base, we have a height, and that's going to allow us to just straight up plug that in here, right? And then we can use our little dx trick, okay? So if you go back here, right, remember we had a circle, and then we use like a little infinitesimal dx. Well, now we can have the same triangle, and then that has a little infinitesimal width. Excuse me, of dx. Whoops, that's kind of not the right way that I wanted. It should be this triangle, right? Because x goes from 0 to 1 over here, and so this way would be dx, right? And so you can just add up all of these triangle slices, all the way this way. So like you'd end up with like a really small triangle right here, but you have a really big triangle over there. So that's method number 2. So now we've used 3 integrals. We've used 1 integral. Well, can we use 2 integrals? And the answer is yes, you can. It is just this. And so if you're looking at this, right? Well, okay, this was way down here, right? And this was back up here, right? I just didn't add the 4, right? So okay, so I guess that's sort of, I mean, it's sort of separate ways, but it's also not. And then what about the 4th way? Well, if you know the formula for the volume of a pyramid, a squared h over 3, and you looked at our coordinates, if you rewind a little bit, you can know that the side length is the square root of 2, and that h is 1, and that by the formula it's going to give you 2/3. Okay, so now the next question. Okay, there's 4 different ways to do this. Some of these ways seem a lot easier, and some of these ways seem a lot harder. So, like, is one way better than the other? Like, are there different situations where these work in different spots or times? Like, what's going on here? Like there's a little more information that needs to be given, right? So first of all, this is a very generic formula, right? It works, but it works in the case of if your pyramid has constant density. Okay, so density is going to be the big theme here of why these are different from each other, right? So if you have a constant density, right, and that density happens to be equal to 1, right, this formula, you're good to go, right? You can find your A, you can find your H, you can plug it in, and if it's a square pyramid, you're good to go. Okay, so, but what happens if we have a variable density, right? What happens if we have more more mass in certain regions of our pyramid, right? It's not uniform, right? Well, you have this here, right? But since this is only a one-dimensional, like, well, I don't want to say one-dimensional, but only an integral involving one variable, right? Your density function can only be a function of x. Okay, right? Like, you can't have a y or a z in your density function because you're only integrating with respect to dx, right? So how will this change if you had a density function? Well, you would just multiply it in here, right? Like, this is still there. Like, this 1/2 times quantity negative x plus 1 squared is still going to be there, right? You just multiply by a density function dx, okay? And instead of getting a volume out, you get a mass, okay? So that's the other thing to think about, right? Is that if you're multiplying by a density function, you get out a mass instead of a volume, right? So, okay. And so then if you come down to the second one, right, well, now you can have a density function of x, y, and of x and y, okay? So now you can have a change in density of two variables, right? And then this one over here, you can have a density function of x, y, and z, right? So that's where these are different, right? Is that if you were asked to find the volume of this, right, of this particular case, I would go straight to this right away, right? I don't have a density function I have to worry about, right? Intuitively, to me at least, right, I can go to this a lot faster than I can to any of the other options, right? I mean, you could use the volume one, right? If you knew it off the top of your head. Otherwise, I'm going straight to this. The second option, I would honestly say, isn't even this one. It isn't even the double integral. It's probably the triple integral to me, because like finding the equation of the plane isn't super intuitive to me, right? It's like I might as well just take it slow and get the z part right, and then do the y part, and then do the x part right. It doesn't immediately jump off the page to me to just plug this in as part of a two-dimensional integral. So that's also, so I wanted to show you this, right? Because first of all, this kind of goes back to, is it an area? Well, no, it's not. We were using multidimensional integrals, right? So it's definitely more of a sum, right? We were summing cubes, or summing areas, or summing circle areas, right? And that, a single integral, a two-dimensional integral, a three-dimensional integral, they ultimately are all part of the same family. And that using a double, a triple, or a single integral often depends on the context of your problem, right? And when you get a problem, knowing, first of all, how many dimensions you have involved, right? Is it 1? Is it 2? Is it 3? And then asking yourself, okay, well, do I have other factors like a density that depend on those 1, 2, or 3 variables, right? Can help you determine, what am I looking to do? Am I looking to do a triple integral, right? Because I've got a density function with 3 variables, right? Or do I not have a density function at all, and a single integral is just going to do me just fine, right? And maybe you have an object, right, where finding the area, right, isn't very practical, right? You have some like oblong shape or something, right, to where it isn't very easy to isn't very easy to find an area, right? So then you kind of have to go over here to the triple integral, right? Like right away, because you don't have an intuitive area, right? So yeah. The last thing that I want to mention, right, is that these were Cartesian examples, right? I think that the next episode is probably going to be on two-dimensional motion. We're going to be going back to motion. But at some point coming up, I think relatively soon, I'm going to be doing an episode on non-Cartesian coordinate systems. And how, right, well, what happens if we have like a circle, right? Or a cylinder, or a sphere, right? You'll quickly realize that using Cartesian to solve those problems is not fun. It straight up is not fun, right? But there's a better way that we can deal with them by using a different coordinate system. And so I didn't show any examples of that here, even though I thought about it. But just know that if you're thinking about like circular regions and like ellipses and ellipsoids, right? And you're like, oh my gosh, how could I ever integrate over something like that, right? There is a better way to do it. And that will be coming. So that is it for this episode. I hope you enjoyed. I hope you learned something new. As always, feel free to like, comment, and subscribe. I'd much appreciate it. If you have any specific questions or you want to go a little more in detail, you can always send me an email as well. So until next time, enjoy your time, and I will see you in the next episode.